In this video, we're going to talk about inverses of functions. The inverse of a function is the reverse of the original function. The inverse of a function undoes what the original function has done. So if the original function is defined as y equals f of x, then the inverse of the function will be y equals f inverse of x. We write it that way. This is not read as f to the exponent -1 of x. It's f inverse of x. Okay, that's not an exponent there, even though it looks like one. That's not, in this context, that's not what that means. Now, what is an inverse? Well, if the point AB is on the curve y equals f of x, then simply switch the x and the y coordinate, and the point BA will be on the curve of y equals f inverse of x. And as we'll see, the way we determine the inverse algebraically is to simply switch the x and y variables in the defining equation of the function. Why is this important? Well, inverses are important because sometimes it's helpful to switch the independent and dependent variables of a relation. For example, suppose that the Lenarduzzi Paving Company charges $10 per square foot for installing interlocking paving stones plus a $50 delivery fee. So using a little bit of grade 9 math, we would see that letting x be the area that Tom wishes to cover in square feet and letting f of x be the cost to Tom, we would see that it's 10 times that area in square feet plus a flat rate of 50. So the f of x, the cost, will be 10x plus 50. So if we were to build a table of values, we would see that if Tom wanted to cover 40 square feet, the cost would be $450. And if he wanted to cover 80 square feet, the cost would be $850, and on and on. Well, this table of values is useful when we know the area that we want to cover and we want to know the cost. But suppose there's another situation where an individual has been saving up money. They know how much money they have and they just want to maximize the area that they can cover. In that case, we'd want to switch the formula around so that we can input the cost and receive the area as the output. In other words, Tom might say, I have $450. What area can I cover? Well, to use the formula as written wouldn't do it for us. We want to somehow switch that around. So our process will be as follows. We're going to write y equals 10x plus 50. And then we're literally going to switch the x and y. So literally just take the, put x in for y and put y in for x. And now let's solve for the y that we now have written. Well, to do that, we'll subtract 50 from both sides, and then we'll divide both sides by 10. And then we'll call that f inverse of x. And so, again, what's the point of this? Well, the point is now, if Tom says he has $450, we can tell him, oh, very well. 450 minus 50 is 400, divided by 10 is 40. We can cover 40 square feet in area. If he tells us he has $850, then we can say 850 minus 50 is 800, divided by 10 is 80. We can cover 80 square feet. So that's why inverses are important. So one more time, the method to determine an inverse is you rewrite the function expression, put in the y if it's written in f of x form. In part 2, switch x and y just like we did. In part 3, solve for y just like we did. And then in step 4, that y, now call it f inverse of x just like we did. So suppose we wanted to know the inverse of this function and we wanted you to state the slope and y-intercept of the inverse. Well, we would simply let y be 3x minus 7. Instead of saying f of x is 3x minus 7, we say y is 3x minus 7. Then we switch x with y, so we'll say x is 3y minus 7. And now we're just going to try and isolate for y. So we're going to add 7 to both sides. X plus 7 is 3y. We're going to divide both sides by 3, and we're going to get our expression. Now, if we're saying f inverse of x is x plus 7 quantity over 3, then instead we could say f inverse of x is 1/3 times the quantity x plus 7. And we almost have it in slope y-intercept form. We could say 1/3 x plus 7/3. Okay, and that's our equation for f inverse of x, and we can say the slope of the inverse is 1/3 and the y-intercept is 7/3, because if you recall from grade 9 math, when you're in mx plus b form, m is the slope and b is the y-intercept. Now, suppose we're told that there's a function with the points 2, 3, 4, -9, and 5, 11. We want to determine the points in f inverse. We want to state the domain and range of f and f inverse, and then we want to say if f inverse is a function. So to determine f inverse, we're just going to switch the x and y coordinates. 2, 3 becomes 3, 2. 4, -9 becomes -9, 4. 5, 11 becomes 11, 5. Okay, so those are the points in f inverse. Now we want to state the domain and range of both f and f inverse. Well, the domain of f will be the domain of f will be the set of 2, 4, and 5. The range of f will be the set of -9, 3, and 11. The domain of f inverse will be the set of -9, 3, and 11. And the range of f inverse will be the set of 2, 4, and 5. Okay, and we'll show it there. Now, something I'd like to point out is notice that the domain of f is equal to the range of f inverse. It'll always be that way. And notice that the range of f is equal to the domain of f inverse. That'll always be that way. So the domain of f is always equal to the range of f inverse, and the range of f is always equal to the domain of f inverse. And that's very logical because the inverse involves switching every x coordinate with every y coordinate. So therefore the effect of that is to switch the set of all x coordinates with the set of all y coordinates. So in other words, the effect is to switch the domain and range and vice versa. For part C, go back and remind ourselves what f inverse was. This is a function because there's only 3 possible x values, and when x is 3, I know y has to be 2. When x is -9, I know y has to be 4. When x is 11, I know y has to be 5. There's never any question. All right, example 2, very similar question. Very, very similar, so we'll go through it a little more quickly. We want to determine the points in f inverse. So if -7, 6 is in f, then 6, -7 is in f inverse. If -2, -1 is in f, then -1, -2 is in f inverse. If 6, -1 is in f, then -1, 6 is in f inverse. Similarly, we're going to state the domain and range of both. And so the domain of f is the range of f inverse, and the range of f is the domain of f inverse. It'll always work out that way. And then finally, we remind ourselves what f inverse is. And now we see, hey, look, f inverse isn't actually a function. Because when x is -1, y might be either -2 or 6 in the inverse function. So even though the original one is a function, the inverse of it is not a function. So as we can see from question C in the last 2 questions, if f is a function, then the inverse f inverse may or may not be a function. In this question, we have a funny looking function. It passes the vertical line test. We're going to graph the function y equals f inverse of x on the same Cartesian plane. So one way we can do it is just to determine the coordinates of key points on the graph, like that. Now, since -5, 3 is on the original function, then switching x and y means 3, -5 will be on the inverse. Since -3, -1 is on the original function, switching x and y, we get -1, -3 is on the inverse. The original function goes from 1, 2, curves up to 2, 3, and then back to 3, 2. So switching all the x's and y's, our function is going to go to 2, 1. Whoops. Is going to go to 2, 1, curve to 3, 2, and then curve back to 2, 3. I just said the same thing, but with switching all the x's and y's. And now might be a good time to recap to connect the relevant points. Negative 5, 3 connects to negative 3, negative 1. So that means 3, negative 5 will connect to negative 1, negative 3. Negative 3, negative 1 connects to 1, 2. So that means negative 1, negative 3 will connect to 2, 1. We've already accounted for this curve portion. And then from 3, 2, the original shoots through 5, 1 with an arrow. So from 2, 3, the inverse will shoot through 1, 5 with an arrow. And it looks like that. So the inverse is the one that's totally written in red. But to show you step by step, a little bit more neatly perhaps, what we do is we've got each of the points listed in blue, 6 different points. What we're going to do now is show the inverses of all 6 of those points. Okay, it got a little sloppy there, but it's really just the inverses of all 6 of those points. And then we're just going to connect them up like we said a minute ago. The original goes from negative 5, 3, from negative 5, 3 down to negative 1, negative 3. So this one will go from 3, negative 5 to negative 1, negative 3. And then since the original goes from there to 1, 2, ours should go from there to 2, 1. And then we curve around like we mentioned a while ago, and then we shoot an arrow through. And this is the function that we get. Now, interestingly enough, the inverse of a function is always the reflection of the original function in the line y equals x. So if we were to draw that dotted line in diagonally, we would see that the red relation, it's actually not a function because the red one fails the vertical line test. Even though the blue one passes it, the red one fails it clearly. But that red relation is simply a reflection of the blue function in the line y equals x.